Power and torque in induction motors. Hello everyone. In this video, I would like to invite you for a conversation about the power and torque in induction motors. And to do so, I'm bringing an exercise for our discussion. I'm going to read the exercise and show you the solution. Let's go. A 460 volts, 25 HP, 60 Hertz, 4-pole, Y-connected induction motor has the following impedances in ohms per phase referred to the stator circuit: R1, R2, X1, X2, Xm. The total rotational losses are 1100 watts and are assumed to be constant. The core loss is lumped in with the rotational losses. For a slip of 2.2% at the rated voltage and rated frequency, find the motors: letter A, speed; letter B, stator current; letter C, power factor; letter D, the power converted from electrical to mechanical; the output power; letter E, the induced torque and the torque delivered to the load; and finally, letter F, the efficiency. As it was going to be time consuming, I decided not to calculate while making the video. I calculated it all beforehand, and I'm going to just present to you the solution. Let's go. Letter A. Letter A wants us to calculate the speed. The synchronous speed is given by (120 times Fe divided by P, where Fe is the system's frequency and P the number of poles. And the result is 1800 RPM. We can convert this number to radians per second. Let's do it. The conversion is 1800 RPM times 2 pi radians for every revolution times 1 minute for every 60 seconds, and then this result is 188.5 radians per second. Now let's do the same for the rotor. The rotor's mechanical shaft speed is which is 1 minus the slip is 2.2%, and this we calculated it to be 1800 RPM And the result is 1760 RPM, which can be converted to radian per second as 1 minus 0.022 times 188.5 radians per second, and then the mechanical shaft speed is going to be 184.4 radians per second. These are the results of letter A. 1800 RPM, 188.5 radians per second, 1760 RPM, 184.4 radians per second. Now let's calculate letter B, the stator current. Before calculating the stator current, we need to find out the equivalent impedance referred to the stator side. Okay? To find the stator current, it's necessary to firstly find the equivalent impedance referred to the stator side. The equivalent impedance referred to the stator side total is going to be the series impedance of the stator R1 and X1 plus ZF, where ZF is the combined magnetization plus rotor impedance. So let's calculate it. Z2, you're gonna need this. Pay attention, you're gonna see why. Z2 is equal to R2 over S plus JX2. R2 is this, the slip is 2.2%, and X2 is this. Then it will be and we find the value of 15.1 phase 1.76 degrees ohms. Why did we calculate this? It is important to find the value of ZF. Take a look at this. ZF is equal to 1 over Z2 plus 1 over JXM. And if we put the value of Z2 that we just calculated here, and if we use the value of the magnetization reactance here, we find the value of ZF equal to 12.94 in the phase 31.1 degrees ohms. Okay? Now that we have the value of ZF, we can combine it with the stator series reactance and find the total impedance. I'm going to show you the equivalent model of the motor, and you're going to see that all these impedances here are referred to the stator side. So Z total is going to be 0.641 plus J 1.106. Okay, the resistance plus J times the reactance plus the value that we just calculated for ZF. And then we find a value of Z total equal to 14.07 in the phase 33.6 degrees ohms. And finally, to calculate what's being asked, the stator current, we do the following. I1 is equal to V phase divided by Z total, okay, which is equal to, you take this value here, 460 volts, you divide it by the square root of 3, okay, because this is a line voltage, we want a phase voltage, and the total impedance is 14.01 in the phase 33.6 degrees ohms. And then ultimately we find the value of, for the current, 18.88 in the phase negative 33.6 degrees amperes. This is the result of letter B, the stator current. Okay? These values of impedances will make sense when I show you the equivalent model of the transformer that is used for the motor. We use for the motor an equivalent model that is similar to a model of a transformer. I'm going to show you after calculating the efficiency for letter F. Now let's go to letter C and calculate the power factor. Letter C, the motor power factor is the cosine of the angle 33.6 degrees, okay, which is 0.833 lagging. It is a lagging power factor. Now let's calculate letter D. Letter D wants us to calculate the power converted from electrical to mechanical and the output power. the expressions that we are going to use to calculate the Pconv and Pout are, I'm going to show you, Pconv is equal to 1 minus S times PAG, which is the air gap power, and Pout is equal to Pconv minus Prot. These Prot are the rotational losses. Okay, firstly, let's calculate PAG. PAG, the air gap power, is equal to the input power minus the stator copper losses. Okay, let's calculate them, the input power and the stator copper losses. The input power is going to be P in, is going to be the square root of 3 times the line voltage 460 volts times the current 18.88 amperes times the power factor 0.833. Okay? The value of the current we calculated for letter B, and the power factor we calculated for letter C. So we already know these values. Then the input power is going to be approximately equal to 12.5 kilowatts. Now let's calculate the stator copper losses. The stator copper losses will be equal to 3 times the current, 18.88 amperes squared, okay, Ohm's law, times the resistance, 0.641 ohms. This, we are calculating the stator copper losses. Then we use the resistance of the copper wires of the stator. And this amount to 685 ohms. Then we already know PAG. PAG is going to be this minus this. Okay? PAG is then approximately equal to 11.8 kilowatts. Okay? Now let's calculate, now that we already know PAG, we can calculate the power converted from electrical to mechanical. Pconv is going to be equal to 1 minus the slip, 2.2%, (11.8 kilowatts). And this is going to be equal to approximately equal to 11.6 kilowatts. with this value here and this value here, we can calculate the output power. So this is the first result, okay, of letter D. Letter D wanted us to calculate this, the power converted from electrical to mechanical. And now let's calculate the output power. The output power is then equal to 11.6 kilowatts minus 1.1 kilowatts, which is approximately equal to 10.5 kilowatts. Okay, so these two are the results of letter D. Okay, the powers. All right, now let's go to letter E, which talks about the torques, the induced torque and the torque delivered to the load. Oh, but first, I almost forgot. Let's convert the output power to horsepower. Okay? Let's convert the output power to horsepower. In horsepower, P out is going to be 10.5 kilowatts times 1 HP for every 746 watts. And we find approximately 14 HP. Okay? Then with this result, we finish letter D. Let's go to letter E now. Okay? Letter E wants us to calculate the torques. The induced torque will be equal to the air gap power, AG, divided by the synchronous speed, and this is going to be equal to 11,845 watts divided by 188.5 radians per second, which is approximately 63 Newton meters. This is the induced torque. Now let's calculate the power delivery to the load, or the output, the torque delivered to the load, or the output torque, which is equal to P out divided by the rotary frequency in radians per second, and it's 10,485 watts divided by 184.4 radians per second, which is equal to approximately 57 Newton meters. Okay, this is the power delivered to the load, or if you prefer, the output, the torque delivered to the load, or if you prefer, the output torque. This is the power delivered to the load. And if you divide it by the rotary frequency in radians per second, using international units here, not English units, international units, you find the output torque, or if you prefer, the torque delivered to the load. And finally, our last objective is to calculate the efficiency of this motor. The efficiency of this motor, and the efficiency of the motor is going to be P out divided by P in times 100%, and this is equal to 10,485 watts divided by 12,530 watts, which is approximately 84%. Okay? This is the efficiency of the motor. Okay? And to finish the problem, I'm going to show you the equivalent model of the motor, the equivalent circuit model of the motor. The equivalent circuit model of the motor is going to be this is referred to the stator side, where here is R1, and from R1 we calculated the stator copper losses. Stator copper losses. This is JX1. This is RC, and from RC we calculate the core loss. Okay, here is the magnetization reactance. Here is R2, JX2. From R2 we calculated the rotor copper losses, and here R2, 1 minus S divided by S, and from this resistor here we calculated the power conv. From here we calculate this element enables us calculate the power converted from electrical to mechanical. Okay, my friends, this was the video that I wanted to make. I hope you guys enjoyed it and learned from it. I am a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye!